Hi kids! Welcome to a new weekly science lab video. Let's finish with our series on Newton's laws of motion, moving to the third of them, the law of action-reaction. Wow, sounds interesting, doesn't it? What does it state? Isaac, please.
To every action there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal in magnitude, and directed to contrary parts.
It actually makes sense.
Yes, it is easy. Whatever draws or presses another, is so drawn or pressed by that other. If you press a stone with your finger, the finger is also pressed by the stone with another force that is the same intense. If a horse drags a stone tied to a rope, the horse, if it can be said that way, will be equally dragged towards the stone, because the stretched rope, by the same effort of relaxing, will drag both the horse towards the stone and the stone towards the horse, and will obstruct the progress of both.
So, recapitulating, Newton's first law points out that forces can change the speed of objects, accelerating them. The second law says that this acceleration is all the bigger the more intense the force applied and the lower the mass of the object is. And the third law states that whenever a force is applied to an object, it responds with another force that is equally intense but in the opposite way. In short, every action has a reaction. This law speaks about a certain symmetry in nature, right? Forces always appear in pairs, and one body cannot apply a force onto another without experiencing a force itself. We can promptly see Newton's third law of motion at work by taking a look to how people move about. Think of a swimmer pushing off from the side of the pool, as outlined here. The swimmer pushes against the pool wall with her feet. The wall then applies an equal and opposite force back to the swimmer, so she accelerates in the way opposite to that of her push. You might think that two equal forces would cancel, and it would be like that if they were applied on the same object or system. But they do not, because they act on different systems. In this case, there are two systems that we could analyze, the swimmer and the wall. Focusing on the swimmer, she pushes the wall with her feet, and it responds by applying on her feet another force equally intense but directed to the opposite way. Thus, these forces do not cancel out because they are acting on different systems. As a result, the swimmer experiences a force accelerating her in the desired direction. Did we get it? Then roll up your sleeves because it is experiment time. This time, you will have to do some arts and crafts beforehand. It's about parachutes. I leave you all the information in the images that I am attaching in this same task. Of course, you will have to adapt the instructions to the materials you have. If you don't have tissue paper, then use another type of paper. If you don't have paper clips, use another thing. And don't use anything that is optional or unnecessary. If you don't have a bicycle air pump, just throw the parachute with your hands. The ability to adapt to circumstances is very necessary in a scientist, and it is a sign of intelligence and creativity. And I don't know any smarter or more creative scientist than you. In the experiments, gravity pulls each parachute down, but the air trapped under the paper slows it down, so it falls slowly. This happens because the parachute itself is pushing with its own weight the air trapped underneath, so the air responds by exerting an equal force but in the opposite direction, thus slowing down the fall of the parachute. The larger the parachutes, the slower they fall, as they trap a greater amount of air underneath themselves. If more paper clips are added, the parachutes will be more stable, and their fall will be even slower. Gravity is the force that pulls objects toward other objects. All objects experience gravity, doesn't matter where they are, yes, even in the outer space. But we will talk about that further ahead. I hope you enjoyed this activity. See you! always appear in pairs.